of India.
Sandeep.
Yes. Tata Institute for Fundamental Research, as I don't. Okay, you're welcome.
Thank you. Yeah. So I think Frank Kelly has visited TIFR, but many of you have not, and this is an invitation to you to come to TIFR. I know we had a plan. But one thing you'll notice if you spend some time there is that there's a cafeteria queue. And I think about this every day. You know, it's a long queue, so how to beat the queue? You know, if you go in the middle, it's always crowded. If you go early, just before it starts, even then there's a queue. So there's really a problem of how to time your queue optimally. So when one of the co-authors was visiting me, we started talking about this, and that's how this work really took off. But you know, the same idea works if you have a concert queue or any other queues, many other queues like movie theaters, going to DMV, etc. But in any case, the framework we are going to consider is we'll have finite but large number of customers. We'll say that the server becomes active at a particular time. So let's call it time 0. Customers can queue up before or after time 0. So that's the flexibility customers have. The cost of a customer is additive, and I'll primarily focus on linear costs. So it's linear in the waiting time and in service completion time. So you want to wait less and you want to have your food as soon as possible, or you want the service to be completed as soon as possible. So we will allow multi-class analysis, so we can have multi-class customers, but just the linear coefficients will be different. And what we found was that if you look at the associated fluid model, then the analysis is far simpler. You know, it's almost trivial. So a great deal of insights come when we look at fluid model, where each customer is going to be infinitesimal, and its effect on the overall equilibrium is going to be negligible. So we'll show that the game in the fluid setting has a unique Nash equilibrium point, and we'll explicitly find this point. We'll show that the price of anarchy equals 2 in the single class setting, and we can get tight bounds for it in multi-class settings, both lower as well as upper bounds. And we'll study some methods to reduce price of anarchy, or reduce anarchy. So that is service time restrictions. You restrict some people to come at different times. This is the kind of things people do, but we can quantify now the benefits. Assigning different priorities to customers, or charging tariffs as a function of time of service. So we'll discuss how all of these affect price of anarchy. Okay, so as I mentioned, one motivation is the long queue at TIFR cafeteria. Other motivations can be passport office, DMV, etc., etc. But essentially, you know, there's a cost to going late, but if you go early, then everyone wants to go early, so there'll be huge waiting. So that's the trade-off we're trying to capture. We'll also study a modification where cost may not be a function of service time completion, but of number of people who come before you. So for example, if you're going to a rock concert, what matters is not when you get in, but how many seats are taken when you get in. So number of people who are before you. So we'll see that that's actually a small modification of what we do. Okay, so that's the TIFR cafeteria queue picture. Okay, actually that's not true. I just got this from a web, but it gives you the idea that you have long queues.
Where is it?
I got this from a web,
But where
but I would imagine it's a religious site in the mountains. You know, it's not at all atypical. It's very typical when you go to Himalayas and you have these shrines, you have such queues. Okay, so literature. So there's enormous literature studying admission control, routing, reneging, pricing, etc. So monograph by Haseen and Habib does a good job of summarizing most of it. In terms of arrival times, strategic view of arrival times is just a single work by Glazer and Haseen in 1983, with total number of arrivals is Poisson, exponential service times, and only waiting costs are considered. But all of this is not done in the fluid setting, so their results are much more limited. Transportation science, so we discovered this later, but they have a substantial and mature literature on this kind of problem. essentially vehicles trying to cross a bottleneck every morning. So how do you time when a vehicle goes? So I'll talk briefly about that at some point during this talk. Okay, so series of queuing systems indexed by n. For system n, we'll have the n customers. Customer I picks arrivals from distribution f sub I. Then when we look at this average arrival profile, we shrink the time and shrink the state space. So then the average number of people coming at time t is converging to f of t. So this is if everybody picks fi as their arrival time distribution. You get this, but we'll be working in the fluid limit, so we'll assume that there's an arrival profile f of t.
So to some extent, the arrival is linear.
What's that?
To some extent, the arrival process is linear in time. To some extent.
Yeah, I mean that's how we are doing it, right? Because the number of people are increasing linearly. So we are shrinking the time, and as n is increasing, the number of people is increasing. We shrink the time and we shrink the state space to get the fluid limit. Service time of each customer is IID. So this is the usual stuff. We'll assume essentially in our fluid model at time t, if the service has, so t is positive, if the server has been busy throughout till time t, then the number of customers served is mu times t. So it's linear again in time, the number of customers served. So when you do this, then the net input process x of t, which is arrivals minus potential service completions, in the fluid model is f of t for t less than 0 because there's no service till that time. And after time, when t is positive, then it's f of t minus mu of t. So then the queue length becomes equal to the net input process for t less than 0. And it's just the deflection, the deflected input process for t greater than 0. So all this is well known. I won't. I have a picture. So in particular, if the queue has been busy till time t, then the queue length process is simply f of t minus mu of t. So that's worth keeping in mind. All right. So you've seen this picture before. But this is to keep in mind that the queue length is f of t minus mu of t if the queue has been busy throughout. So we'll argue that that's going to be the case in the equilibrium. Okay, so when to arrive? So suppose now the arrival profile of all the customers is f, and wft denotes the waiting time of a customer that comes at time t. So we'll assume that the cost of the customer, cost incurred by the customer, is linear in the waiting time and linear in the time at which the service is received. So that's t at which time you arrive plus the amount you wait. So it's first come first served. And when we have multi-class customers, then these alpha and beta will be class dependent. So the issue then is what time to come, and more generally, if a person is choosing her arrival time by a distribution g, then this is the expected cost, and the problem is to choose the optimal g which minimizes this. Okay, so Nash equilibrium in this setting is, so each customer now is infinitesimal point in the interval say 0 to 1. So each customer S chooses their distribution G sub S. If the arrival profile is well defined, f of t, so that's just the average of all the arrival profiles of each customer, then we say that this multi-strategy arrival profile is a Nash equilibrium if the cost of when you use G of S is better than the cost for every customer S. If he uses G of S, then he gets a lower cost than if he uses any other distribution for arrival, given that F is the overall arrival profile. So this is clear, right? So suppose everybody uses strategy G of S, then there's an overall arrival profile f of t that we get. Under this arrival profile f of t, so once this arrival profile is fixed, then my waiting time is going to be fixed, so my cost is going to be fixed at every time t. So this set of arrival profiles is going to be in Nash equilibrium if we have this inequality, and you can see that under Nash equilibrium, at each point where I put a positive mass, my cost should be equal, because if it's not, then I can improve. So essentially what I'm looking for is an arrival profile F such that CFT is constant on its support and higher everywhere else. So one can, just work out the details, but essentially the problem is you search for arrival profile F so that along its support, whenever you come, the cost is constant, outside it's higher. It's at least as much. So that's what we're going to take here. You can show the equivalence between these two, but that's what we'll take going forward. So once we accept that, then there's some easy useful insights to take forward. So one is that let's define T star as the first time the server has spare capacity, meaning server is not fully occupied. So f of t is less than mu of t. F of t is the number of people who have arrived. Mu of t is the amount of people served by time t. So first time that f of t, which is really the number of people served. This is the first time the server actually has some capacity available. So the one point to observe is that this T star must be equal to 1 by mu. So what I mean by this is that if I have 1 unit of customers coming in that are served at rate mu, if I serve them throughout, then I need time 1 by mu to serve everyone. In Nash equilibrium, it cannot be that server has spare capacity before this time 1 by mu. And the point simply is this, that so server starts at time 0, it needs this much time to serve everyone. It can't be that you have an arrival profile where some people come later, because then they can come earlier whenever there's spare capacity and reduce their cost. So it's no longer a Nash equilibrium. So in Nash equilibrium, it must be that the server is busy right up till time 1 by mu. Otherwise you can do better. Similarly, you can't have a arrival profile where you have a jump. So I'll just bring that point up. So there can't be no point masses in F. In the sense, if F has a point mass, then that cannot be a Nash equilibrium. Because think of a person who's coming just before that point mass occurs. So you can always improve your cost by, rather than coming at that time when there's point mass, just come a little before it. So, so this F that we are looking for has this property that the server is going to be completely busy till time 1 by mu, and there won't be any point masses. So if we ignore the fact that F can be singular, then it's clear that F must have a density. Okay, now once we accept that, then my claim is that the waiting time under equilibrium profile at any time t must be given by this expression, ft by mu minus t. And the way to think about this is, suppose I come at time before 0. So suppose I come at this time t, then I have to wait this much minus t amount. At this time service starts, and I have to wait for ft by mu people to get served before my turn comes. So my waiting time is going to be ft by mu minus t. And if I come at some time later here, at time t, I have f of t people who will come before me. They will be served at time f of t by mu. So my waiting time again is f of t by mu minus t. Because server is going to be busy right through. So that's the underlying idea. So under equilibrium profile, waiting time is going to have that expression. So we look at the cost. So all of this is under single class right now. So if you look at cost of customer arriving at time t, that's given by this expression, which simplifies to this expression over here. Now under equilibrium profile, this cost has to be constant, and f of t has a density. So one can see that the density is going to be constant. Right? For this to be constant, this has to be constant. So f should in particular be uniformly distributed. So in a picture, the equilibrium profile in the simple setting is going to have the following flavor. We know that the server is going to be busy till this point. So that means the person who comes at this point will have no waiting, will come at this point and get served immediately. That customer's cost is going to be beta by mu. Beta is the linear coefficient of time to completion, so his cost is beta by mu, and that fixes the cost of everybody. So in particular, this person who comes here has pure waiting. The first person to come has pure waiting, so that cost must also be beta by mu. And the arrival rate must be constant, just given by the previous equation. So indeed you get this uniform profile. So this will be Nash equilibrium, and this will actually be unique Nash equilibrium in this setting. So any questions so far? Or? Okay. Now one looks for socially optimal solution. Clearly, if you're looking for socially optimal solution, you don't need to make people to wait. If a centralized person is optimizing, you can always send people exactly at the time when their service is due. So you reduce the waiting time. So waiting time will be 0. And you can again argue that the server must be busy throughout between time 0 and 1 by mu, because if there's a gap, then you can improve your cost by making people come in that gap. So if you're looking for a socially optimal solution, there should be no waiting, and people should come, right up till time 1 by mu when everybody is served. So that tells you that the overall cost is going to be, so that immediately tells you what the social optimal solution is. One social optimal solution is just come uniformly between 0 and 1 by mu. So everyone comes uniformly between 0 and 1 by mu. You come at rate mu, you get served at rate mu, there's no queue. So in particular, the average time to completion is just 1 by 2 mu. So what you're looking for then is that the overall cost is beta by 2 mu. So in particular, price of anarchy is equal to 2. So price of anarchy in this setting is equal to 2. Okay, now, so I won't go through the analysis for multi-class customers, but this picture says a great deal. So this is the case when you have 3 classes of customers. We sort them on the basis of the ratio beta I by alpha I, and the claim is that in the Nash equilibrium, beta 1, the highest ratio will come first, so on and so forth. This will be the profile. This is how the queue will look like. And to understand this, see, the point is this. So what we are saying is that under Nash equilibrium, these classes come in a disjoint manner. So when you're coming in a disjoint manner, using the argument exactly what I said earlier, the arrival rate for each class must be constant. Arrival rate is constant, service rate is constant, so the queue is going to decay in a linear manner, right? So now suppose that the red class is coming as this picture shows. They start building up at this point, then they start getting served at this point. They get served, all of them, by this point. Now if a person is of a blue class, he can come at this time or at this time, any of these points. His cost is going to be constant. But now extend this line. Now if he comes at this point, because the red is coming before it, the cost will be higher. This is the ISO cost line for the blue class customers. So its cost will be higher if it comes here. Its cost will be higher if it comes here, if the green is coming as follows. So that kind of tells you that for blue class, if everybody else follows the strategy that they do, then indeed coming any time between these 2 points is the Nash equilibrium strategy. Similarly, you can see for red class, it has no incentive to come outside of this interval. Similarly for green class. So indeed, they order themselves in this framework. Okay. So now one can do the math on this. So for social optimal cost, one can, it's a simple argument that people with higher beta will come before people with lower beta, because people with higher beta have higher cost for the same time of arrival. So it makes sense for them to come earlier, and people with lower beta will come later. So price of anarchy is an easy calculation. So when all the alphas are equal, price of anarchy comes out to be 2. Otherwise, if you define your Gij in this manner, then one can define bounds on price of anarchy simply in terms of alphas and betas, independent of how many proportion of people which belong to class 1, class 2, so on and so forth. So one can develop these kinds of bounds. So this is of some use just in terms of when you control price of anarchy, one can say concrete things. So now I'll move on to, again, back to single class settings, and then keeping things very simple, we'll start to answer some questions. So how does one reduce price of anarchy from 2 to something lower? So just to concretize that, so one idea is you have service time restrictions. Tell people to come at different times. Certainly when we apply for an application to get a UK visa to come here, you're given, a lot of people are given a time slot. So that's essentially the same spirit. You're trying to have time restrictions on when people can come. So suppose 1 minus a proportion is allowed to be served after time a by mu. So these are carefully chosen times. Then the first a proportion, which has no restriction, has no interest, will simply ignore the other class and come as follows. This is how the queue length will look like. So they'll queue up a little bit early, they'll finish here. And the class which has restriction cannot come before a by mu, cannot be served before a by mu. So for them, it's as if server begins to service at this point. So they'll come in this manner. So one can now see that a proportion of people are coming and their cost is a by mu, beta times a by mu, and 1 minus a proportion is coming at this time. So cost of these customers is given by the cost of customer who comes at this point. Cost of these customers is given by customer who comes at this point. So you get the price of anarchy in this setting. So price of anarchy has that expression over there. In particular, it can be optimized to a equal to 1 by 2. So as you'd expect, it's symmetric. So the best thing to do is ask half the people to come half the time later. And when you do that, you're looking at price of anarchy of 3 by 2. What's interesting is if you were to actually perturb this point, because we don't really know, we don't really get these numbers right. So suppose we ask these people to come not at time a by mu, but a little bit earlier. So when you tell people to come a little bit earlier, interestingly, this class doesn't change its behavior at all. It stays the same. These people now start coming earlier. Right? So if class 2 is asked to come at some time before a by mu, then class 2 continues to come like this, but class 1 now starts coming before that time tau. So that they don't want to be in the same queue as the class 2 people. So that continues up till a threshold point, a star. So when you do that, as you move the threshold in this direction, the price of anarchy increases from 3 by 2. There comes a threshold at which the price of anarchy is equal to 2. And now population 1 doesn't care anymore. So now you have multiple equilibrium after that. So they can spread out. So the point of all this is that all this analysis is quite straightforward in this setting. One can say interesting things. So there's actually a phase transition which occurs at a particular time. I have the expression in the paper. I don't have it with me right now. So in any case, one can just build upon this idea. So if you ask m by n proportion of population to come after n minus m by mu time, so now we have segmented the population in n different segments. Then you can do similar analysis and see that price of anarchy is going to be n plus 1 upon n. So it's going to 0 and it's going to 0 at the rate 1 by n. So that comes out clearly here. One could have also achieved this differently. We could have just assigned different priorities to two classes of customers. So one class of customer has higher priority over the other class of customers. Then since they have higher priority, they prefer to come like this. And given that they're going to come like this, class 2 has no option but to come like this. So you achieve similar results even by assigning different priorities to different customers. And that's kind of in flavor of what we do when you're entering an airplane. People with seats in the back are given a higher priority over people with the seats in the front. Okay. So reducing price of anarchy by differential pricing. So we notice that in this setting, for example, we know the difference in the cost of people who are coming here and people who are coming here. So this is by diktat. You're telling people to come later. But the point is, can one achieve the same thing by just having differential prices? So for example, if we charge the class people who come between time 0 and 1 by 2 mu, if we charge them amount beta by 2 mu, then the same population, so all of this is in a single class right now, I'm just keeping things simple. So the same population will bifurcate itself into two, and there'll be a green population which comes between 0 and 1 by 2 mu time, so it pays an extra amount. And then there's another population which comes after time 1 by 2 mu, So it doesn't have to pay that extra charge. But what you see is that if we didn't have this differential pricing, then this would have been the queue profile, the red one here. But now since we bifurcated the populations, the profiles are as follows. So overall queuing cost has come down, and one can again see that the, just as before, that the price of an key is going to be 3 by 2. We're assuming all the money that's paid by this class is used for social benefit. So that doesn't come in the price of an key calculation. But that again comes out to be, so beta equal to 2 by mu, you get price of an key of 3 by 2. The only thing with this system is that, you have to worry about incentives of everybody. So person who's charging you price for coming, people who come early, he's charging them higher price. He has incentive to overcharge. So if you were to charge P greater than beta by 2 by mu, so now less people, same class of people, less people will come here, more people will come later, and again they'll organize themselves in such a way that if the cost paid by this class, which is same as the cost paid by this customer, and the cost paid by this class, which is same as the cost paid by this customer, the difference is exactly the P that the customer is, that the manager is charging for people coming early. But what's happened now is that although the canteen owner, the system manager, I guess, is making more profits, his revenue increase from before. They optimize that P equal to 3 by 4 beta by mu. The overall system performance is degraded now. In the sense you have a gap in service here, and the service goes on much longer. So we haven't done this analysis in any depth, but one can kind of say a lot about incentives and how that affects the system. On the other hand, if the amount charged is lower than the correct amount, which is beta by 2 mu, if the amount charged for people coming earlier is lower than that, then more people would want to come early to take advantage of early service. So profile will now look as follows. Again, the idea is that person who comes at this point, who gets served here now, and the person who comes here should have the same cost, and that defines the whole profile for you. So again, the more you decrease the price from beta by 2 mu to 0, higher the price of anarchy is going to be. At some point there'll be a phase transition and you'll achieve this red profile. So all this can be established. Okay, now if we were to, as I mentioned earlier, one can also look at another cost structure where cost is a function of your waiting time as well as not the time of service completion, but number of people who come before you have. So instead of T plus WT, if we have beta times F of T, well, one argues the same way that even here, server will be busy throughout the time that there are people in the system, so it'll be serving at a full rate. So the overall cost will now will have a similar expression to before, except that instead of having beta here, now we have beta hat, which is beta times mu. So all the results that I've said generalize to this setting as well. So price of anarchy in particular in the single class setting remains 2. Okay, so one question of course is, how good are these asymptotic results? So certainly fluid limit gives results very cheaply, but how representative are they of finite n? So what we've done here is just done a simulation for finite n, and then we've normalized the time and normalized the cost. So normalize the queuing system and normalize the time, so hence normalize the cost. So you see that, so what we are looking for is that if indeed we were close to the equilibrium profile, then no matter at what time I come, the cost should be the same, should be constant. Under equilibrium, that's the thing that arrivals see the same cost everywhere. So here we see that when we have 10,000 customers, then that's true. That any time between this threshold that the theory tells us, and this is just 1 by mu here, the cost becomes more or less constant. But for small n, for n equal to 10, it's, the cost is much higher for coming later than for coming earlier. and around n equal to, I guess, 1000, you begin to see this asymptotics kicking in. So here what I've assumed is as follows. I've assumed that the service times are exponential, and each person is arriving by, the asymptotic policy tells you that the overall arrival profile should be uniform between 2 points. Now that uniformity can be achieved in a variety of ways. If everyone chooses to come in a deterministic time interval, then also the overall profile can be uniform. And if everyone chooses to come randomly, then also the arrival profile can be uniform. So in this case, we are assuming that everyone is sampling randomly uniformly between those 2 points. So that's a more noisy system, and service times are exponential. That's also a little noisy system. So in that case, you see that convergence is a little slow. What this is actually suggesting is that the arrival. So let me explain a little bit more. I made a mistake. So what I'm saying is that suppose there are 100 people. All the 100 people are coming following this asymptotic policy. So they are coming uniformly between these 2 intervals. So if they are following this uniform asymptotic in the equilibrium policy, then what will your cost be if you come at different time intervals? And what this is saying is that the cost is higher if you come later. What this suggests is that for the finite n case, people should not have a uniform profile, but they should have less weight on the end here, so that a tagged customer, a person who arrives at any time, sees uniform cost. So is that kind of clear? That for finite n equilibrium policy, it will not be uniform. It will actually have lesser weight towards this end, so that a person coming at any time sees a uniform cost everywhere. So that's a suggestion that comes from here, and as you'd imagine that this correction that you do reduces with the increasing n. This can actually be proved. We've actually done that now, at least in simple settings, but in this work I'm not talking about that. Okay, so if you have less noise in the system, so suppose the arrivals are approximating a uniform profile, but they're coming deterministically. When most of us, when we go to a cafeteria time, we kind of come deterministically. We make small perturbations to improve our cost, and the net effect one hopes is that you have an equilibrium profile. So that's another way to achieve an equilibrium profile. So indeed, if arrivals are coming deterministically and service times are uniform with variance which is less than before, say 1/12 of before, then you see far faster convergence. So even at n equal to 100, the equilibrium profile that we derived is pretty close to what the equilibrium profile would be for n equal to 100 case. So numerically, you get a sense of convergence to the equilibrium behavior. So any questions on this, or is this kind of clear? Okay, so this chart is interesting. It's from transportation literature by Lindsay, and it says what the equilibrium profile will be when people have nonlinear costs. So the picture is as follows. So we have 3 classes of customers here. Say the blue class fixes its overall cost. So it's an ISO cost curve, and says at this time, how much waiting time do I need to achieve this cost? So that's how I'll drive my blue curve here. Similarly for red class, similarly for green class. And now the point is that the upper envelope that you see is an equilibrium profile if the capacity requirements are given by wherever you achieve the. So what that means is that red should come wherever it's on the top, blue should come wherever it's on the top, so on and so forth. So this is the time at which red is getting served. Yeah. So yeah, I should maybe correct. So if I'm getting served at this time and my cost is specified, then how much waiting should I have incurred to get this cost? So that's how I write these curves. So in any case, so for this much service for red, this much service for blue, this much service for green, this is indeed the equilibrium profile. And you can see again why, because if red and green are coming as follows, then blue customer has no incentive to come in this interval or in this interval. So similar logic gives this profile to you. What's interesting about this, so this analysis is very nice, and what they do is they prove existence and uniqueness results without giving computational algorithms. Turns out that it's very easy to devise simple computational algorithms which actually find. So what they have not done in this picture is that what the services that you get follow from the cost that you specify. Not that other way around where you specify that this class needs so much of service. Now what should the cost be? So the other problem is for the other problem which is important, they have existence and uniqueness results, but we develop computational results, and the idea is straightforward. We look at all these classes of customers, red, blue, and green. They have capacity requirements, so red needs to be served for so much fraction of time, green needs to be served for so much fraction of time, blue for so much fraction of times. So we know that. We'll take each curve, raise it until it gets its service requirement, keep it there, go to some other curve, raise it till it gets its service requirement. When I move one curve up, it eats into service of other classes, but the overall service that's given to these classes increases. So one can come up with a sequence of increasing. So when I raise a curve, the cost also increases, and the capacity assigned to the total capacity assigned also increases. So that's a non-decreasing sequence of numbers. So one can use that to prove that this simple algorithm actually achieves the capacities that you want. So again, let me just say it very quickly. We have three classes. Suppose we know that red wants some amount of capacity, blue wants some amount of capacity, green wants some amount of capacity. The way we'll come up with an equilibrium is we'll start with zero allocation to all of them, increase one by one, we'll increase each class. We'll increase their cost until they achieve the capacity that they need. We'll do it for one, then we'll do it for another class. When we do it for another class, it gets more capacity, but it eats into capacity given to other classes. But the overall capacity increases. So one can show that this algorithm will actually converge, and it will actually converge to a unique point. So in any case, that's easy thing to show. So upper envelope gives equilibrium schedule, and computation are going to solve these capacities. Okay. So other than that, I guess I have a little bit of time, so I can say that what we now have is, so it's work in progress, but we can solve the finite n case. Turns out it's not as difficult as one would imagine. You don't get explicit expressions, but you can show that it exists and it's unique and it converges to the fluid limit that we have. So one can actually talk about that. And we also have results which are not so difficult if we say that even in the fluid limit, the number of customers in each class is not fixed, but it's random. So one can see interesting things in that setting as well. Okay, so in conclusion, we consider a queuing model which occurs in a variety of settings. The customer strategically selected their arrival time distributions. So we looked at this in a fluid setting, and in fluid setting we got far greater tractability. In particular, one could come up with strategic arrival profile in that setting, even in the multi-class customer setting. And I should also add that if the number of classes is not finite but infinite, the analysis is straightforward. One can still get expressions. And even then we can bound the price of anarchy in that setting as well. And we discussed some ways of controlling the price of anarchy. And then we discussed briefly the nonlinear cost case. Yeah. Thank you.
All the customers are paying penalties for not meeting individual deadlines. It's a similar problem in fluid limit, or seriously different.
I would imagine it's similar. I would imagine.
Could you just sketch how you would sort it out? Suppose the problem is that you want a fluid limit. The problem is the fluid limit. Each has individual deadline, pay penalty if not met. What will be the procedure?
So now, but the penalty would be linear or would it be?
That's up to you. I imagine you say linear.
If it's not linear, you cannot.
Okay, linear.
No, I would imagine nonlinear is not so difficult, but I think that at the end of it, you're looking for iso-cost profiles, right?
Okay, what kind of answer you expect in this station?
Well, this picture already gives quite a few answers. If you, for that customer, for each profile, if you were to draw an iso-cost curve, right? If you do it for each and every, that gives you at least a profile of the equilibrium solution. Now you have to kind of work out the explicit, numbers to see exactly when you get the right capacity that each class needs. But this, this picture already makes things much clearer in terms of We can discuss maybe later in more detail, but but generally my experience,
It's simple question.
it's a simple problem. Yeah.
I was going to ask, the case you described with random arrivals
Yeah.
rather than just the uniform arrivals. So the cost went up towards the end, and that's presumably because the randomness produces some sort of excess queuing.
That's right. That's right.
And that is felt towards the end.
That's right. Yeah.
And I'm just wondering, I wasn't quite clear what the curve meant, because one would expect, therefore, the individual customers to, their reaction to be to shift themselves
Yeah.
further to the left.
So we don't answer that here right now.
Right.
It's suggested by this picture, but that's indeed true. So that's kind of so for finite n, the equilibrium policy will have this characteristic. There'll be less weight on this side, and there'll be some weight outside of this point.
Right, because and then that, corresponding to the fact that there'll be some positive probability that there'll be idleness early on.
Yeah, I mean, that makes all the difference. So that probability, you have to show how it converges to zero as the number of people increase.
Right, but one still got the definition of a Nash equilibrium or a Bayes Nash
Oh yeah,
equilibrium.
yeah, absolutely. Yeah, and that probability at any time t of q being empty plays a major role in that strategy. In the finite, that's correct.
Let me give some information. So just